Welcome to the Explainer. Today, we're going to break down two of the biggest ideas in math, relations and functions. We're going to strip them back to see how we get from just pairing up random things to building powerful rules that honestly run a lot of the world around us. So here's our game plan. We'll kick things off with the absolute basics, sets and relations. Then we'll dive into how to sort and classify those relations. After that, we'll see how a special kind of relation becomes a function, and finally, we'll check out the different flavors of functions. All right, let's start at square one. How do we even begin to create a mathematical link between items from two totally different groups? Okay, so picture this. We've got two simple lists, or sets, as they're called. Set A is a bunch of cities, Agra, Chennai, and Bhopal. Set B is a few states, UP, Tamil Nadu, and Haryana. Right now, they're just two completely separate lists of words. Our mission is to connect them in a meaningful way. First, before we get all specific, let's just imagine every single possible pairing we could possibly make. You know, Agra with UP, Agra with Tamil Nadu, Agra with Haryana, then Chennai with all three, and so on. This giant collection of every single possible pair is called the Cartesian Product. It's basically our universe of all possible connections. Now, this is where it gets interesting. We don't really care about all the pairs, just the ones that follow a specific rule. So let's make a rule. The city is in the state. All of a sudden, most of those pairs we imagined just disappear. Agra is in UP, so that pair gets to stay. Chennai is in Tamil Nadu, that one's a keeper too. But what about Bhopal? Well, it's not in any of the states we have in set B, so it doesn't get paired up at all. This new, much smaller, filtered group of pairs, that's what we call a relation. And honestly, the best way to see this is with an arrow diagram. It just cuts through all the noise. You see our cities on the left, our states on the right, and the arrows show only the connections that actually follow our rule. An arrow from Agra to UP, an arrow from Chennai to Tamil Nadu. That's it. Simple, clean, and you get it instantly. So now that we know what a relation is, we can start to organize them. Turns out, they have different properties, almost like they have different personalities. All right, let's clear up something that trips a lot of people up, the difference between identity and reflexive relations. It really all comes down to how exclusive they are. Think of an identity relation as a super strict club. It has only the twin pairs, like 1-1, 2-2, and nothing else. No plus ones allowed. A reflexive relation, though, is a bit more relaxed. It has to have all the twin pairs, that's a requirement, but it can also have other pairs, like 1-2, hanging around. Next up, we have the symmetric relation, and this one is all about balance. The rule here is dead simple. If you have a connection going from A to B, you absolutely must have the return trip from B to A. For every single pair, you need its mirror image. It's got to be a two-way street. Now, a transitive relation, think of it like a logical domino effect. If A is connected to B and B is connected to C, a transitive relation says there has to be a direct shortcut from A to C. If you can get from A to B and B to C, then the connection from A to C has to exist. It's like a chain reaction. So what happens when one relation manages to do all three of these things? If it's reflexive, symmetric, and transitive? Well, then it earns this special, really important title, an equivalence relation. This is a super powerful kind of relationship that lets us group similar things together. Okay, but what if we make the rules even stricter? Well, that's when we graduate from the world of relations into something even more precise, and something that's absolutely critical in science and technology, a function. And here it is, the absolute, golden, non-negotiable rule of a function. Every single input can only have exactly one output. An input can't be indecisive. It gets one arrow to point and one arrow only. That's the law. But, of course, it doesn't stop there. Even inside the strict world of functions, there are different categories. So, let's quickly break down the main types you're going to run into. First up is the one-to-one function. You might also hear it called injective. The easiest way to think about this is like assigned seats at a wedding. Every guest, that's your input, gets their own unique chair. That's the output. No two guests are allowed to sit in the same seat. Everybody gets their own. And if you look at the arrow diagram, it becomes super obvious, right? Notice how no two arrows starting from the left end up pointing at the same spot on the right. Each input has its own exclusive destination. That's the visual test for a one-to-one function. Now compare that to this. See how two different inputs are pointing to the same single output? This is what we call a many-to-one function. Now, it's still a perfectly valid function. Remember, each input has only one arrow coming out of it, but it fails the one-to-one test because an output is being shared. All right, next type, an onto function, also called surjective. The rule here is all about the destination set. For a function to be onto, every single possible output has to be hit by an arrow at least once. There can't be any lonely, unused elements just sitting there on the right side. And again, the arrow diagram makes this crystal clear. Just look at the right-hand side. Every single item over there has at least one arrow pointing to it. Nobody's left out. That's the telltale sign of an onto function. So what if a function is a total overachiever? What if it's both one-to-one, so no outputs are shared, and it's onto, so no outputs are left unused? Well, then you've got the gold standard, a bijective function. The result is just a perfect pairing. It's a clean, one-to-one correspondence. Every single element on the left is perfectly matched with a unique element on the right, and every element on the right gets used exactly once. It's a perfect match. And that leaves us with a final thought. I know these rules can feel a little abstract, but they are everywhere. Seriously, think about systems you use every day, like your social security number, or a student ID, or the VIN on a car. Why is it absolutely critical that those systems follow a strict one-to-one rule to work? It's something to think about.